thank you, Steve and Boise, for inviting me to give this talk. It's 6:30 in the morning, so it's actually not terribly late, terribly early. Or maybe it is terribly early. I just want to give you a brief introduction to the lab that I started in 2014 when I moved to Hawaii. I was in Chicago for about 22 years before I kind of realized, maybe I don't like snow as much as I thought I did. And I went to warmer climates. So in a nutshell, what the laboratory does is data visualization. But the other hat that I wear is I am the co-director of the Hawaii Data Science Institute. And of course, many of you are hearing the widespread proliferation of interest in data science, especially large companies that collect large amounts of data and are trying to make sense of them. So now is a good time to be in this field of data science, which I believe includes data visualization. The kind of work that I do, and actually Steve has a long background in this too. We think of ourselves as the builders of modern day microscopes or modern day telescopes. If you think back to when you were like in high school, the microscopes that you use kind of look like this on the right? And today, if you talk to any computational scientists who collect data from sensors like in the oceans or telescopes pointing at the sky, these are the new light sources of this notion of a microscope. And because the data that's collected is so large, you literally need some kind of supercomputer to do all the processing and to filter down things that are interesting to you. And of course, that becomes the magnifying lenses that are part of the microscope. And then lastly, at the top here, where the user is actually looking through and turning the knobs, this is where visualization sits. And so you can sort of see why it's so important as part of the scientific enterprise to have all these things connected so that people can get the science done. So as a data visualization person, what's important to me is that I have access to collaborators who work in these scientific fields. I collaborate with folks in the HPC area, because without these, as a visualization person making lenses, I have nothing to look at. So I guess lessons for students is try to collaborate more. Okay, so I characterize the thing that I focused the most on in my career has been on trying to manage the scale and complexity that's growing in data and information. These are some old classic photos I took almost like 20 years ago, where you have in Disney Studio, they use all this wall space to put up pictures of their storyboards so they can figure out how to tell a story or how to make their next motion picture. This is Al Gore when I think he was still vice president at the time, or maybe after that, where you can see he's primarily working on these displays, and his desk is pretty much useless for actually work. It's completely cluttered with papers. This is BMW, and they have this wall of inspiration where they basically take pictures of images that they find that's inspirational in architecture, automobile design, and fashion, because a car is always seen in the context of its background and the people who are driving it and what they wear. So they have to be very conscious about trends in these kinds of design aesthetics. And then just for fun, I took a photo of one day of some staff and students in my lab in Chicago who were working on this giant jigsaw puzzle together. You can see sort of this parallel processing going on where somebody's like expecting the big picture, they're clumping the bits of the puzzle into different colors, and then they're starting to build the borders around the puzzle, right? So this is a perfect example of this kind of information management task, right? So if you have done it, jigsaw puzzle, you understand the problem. And so where all this started was in 2000 when I started doing this work in something called the Continuum. And essentially, it's kind of like a smart room where we transform all this analog stuff into a digital form. And so back then, these displays were pretty expensive, and they were only plasma. Plasma displays were the only ones possible. And then the LCD displays were, pretty small, and they had these giant borders. This particular display is projection, but we're projecting stereoscopic 3D. So this is actually a 3D object floating in front of you. And so this project was called the Continuum. And when we developed the space, the goal was to try and see if we can build a digital analog of these kinds of spaces and see if people can be productive or more productive in them than this traditional analog kind of space. Fast forward to 2021. When I moved to Hawaii in 2014, I started a project called the Cybercano, which stands for Cyber-Enabled Collaboration, Analysis, Navigation, and Observation Environment. And basically, it's another name for a tile display. These kinds of displays are getting cheaper and cheaper to build. You're seeing more and more displays in universities, in laboratories, even in classrooms. I use this to teach class when I teach my visualization class. And the software that we use to drive it is something called SAGE, which I'll talk about a little bit more, I think, in the next slide. And yeah, let's jump right into it. So I'm going to play this very brief, like 2-minute video about SAGE, just to give you a flavor for what it's like to work in front of a tile display wall.
SAGE2 is the world's most advanced software for teams to collaborate while immersed in information, helping you make decisions with greater creativity, speed, accuracy, and confidence.
Hold on, waiting for the trash truck to go by. Morning trash pickup.
SAGE2 is the world's most advanced software for teams to collaborate while immersed in information, helping you make decisions with greater creativity, speed, accuracy, and confidence. To begin collaborating, you simply connect to a SAGE2-enabled display wall using a web browser. During a meeting, you can drag and drop content to the wall and interact with it all from within your browser. It's that easy. You and your collaborators can even connect to the same wall at the same time and share documents or entire laptop screens. Working over distance? No problem. It's easy to connect remote team members with video conferencing. Use your favorite browser-based video conferencing tool like Google Meet or Appear In. Want to share documents with your remote team? Just drag them to their walls directly. For example, we can share a PDF document, fill the whole wall with it, and everyone can point to it and flip through the pages. You can even share laptop screens with them. Not just one laptop screen, but as many as you want at the same time. Now, with artificial intelligence, you can even talk to SAGE2. Search the web for Hawaii. Launch Google Maps. Go to University of Hawaii at Mānoa. Zoom level 18. If your team uses Google Documents or Microsoft 360, it all works in SAGE2. Type into your laptop document and all the changes can be viewed live on the wall. Play 4K videos too. If you need to do some brainstorming, use Post-it notes or sketch ideas with a doodle pad. Everything you put on the wall can be saved as a session, so you can resume your meeting at a later time and bring back all the content from before. Running apps on a big display wall just gives you more thinking room. Setting up SAGE2 is easy too. All you need is a computer and displays. No special hardware needed. All the magic is in the software, and it's open source too. And speaking of software, many web apps will also readily run in this environment, such as the following. SAGE2 and its predecessor, SAGE, have been developed with over 15 years of research funding by the National Science Foundation to help scientists accelerate their research. But now it is so much more. Today, it's the most widely used collaboration platform in the world for big data and big picture analytics, helping users gain insight and knowledge. It is used for classroom teaching, for brainstorming sessions, for weekly meetings, for presentations where just one PowerPoint projector just isn't enough. Work at the speed of imagination. See the big picture in your collaboration. SAGE2.
So I hope that gives you a little overview of what it's like to work in front of a SAGE environment. What people have done is to take those kinds of capabilities and start to explore how are people benefiting from the use of these kinds of systems. And what we've noticed is that people do come to decisions with greater speed, accuracy, comprehensiveness, and confidence. And what I mean by that is, these are a bunch of cited papers. And by the way, for the students out there, in the next slide, I'm happy to share all these slides with you. The next slide I actually have all the paper citations so that if you want to go and read up on it, you can find out more. But the real cool thing about having these large displays is that you're able to see detail and context simultaneously, right? You don't have to flip back and forth between windows. For a large group of people, it helps you externalize your working memory, right? Everyone's working in front of the wall, thinking about ideas, thinking about thoughts, and they're able to take the thoughts and post it on the wall and share it with everyone simultaneously. And that little picture I showed you with people, putting the jigsaw pieces together. Well, large display walls, we found that they do increase parallel processing among work teams. It also improves location memory of information. And we also found that it helps performance keep pace with increasing data size, what we call perceptual scalability. And in the end, what we also find is that there's greater confidence in the conclusions that you make because you're seeing more of the information and you feel better that you haven't missed anything that might be important. And lastly, and perhaps the most important, is that you're now starting to see what is the bigger picture, what is the higher level pattern in the data that you wouldn't be able to see if you just had a small screen. As I said, these are the references. Go read up if you're interested in getting into more details about these findings. So then the pandemic happened, right? And when the pandemic happened, people couldn't go into labs anymore to use their big display wall, right? And so it's like, what do we do then, right? So here's something fun that we did. We did a little study asking people what they felt about using SAGE2. These are all SAGE2 experts, but also these are people who have gone to presentations and board meetings where they use a PowerPoint projector as the sole form of information sharing. And we asked them to compare against their experiences with just using a classical projector in a regular meeting room. And then post-pandemic, since a whole bunch of people have had experience using Zoom, we asked them to rate their Zoom experience as well. And so in the kinds of questions we asked them, how focused were you in the meeting? How much did you contribute content to the meeting? Did you find it easy to contribute content? Did you get sufficient feedback? Did you find it easy to make suggestions? Did you enjoy using the technology? Did most participants appear to listen to each other? Right? Did most participants contribute content at appropriate times? Body language, was consensus reached? And what we found was that people who were using SAGE2 tended to lump things on the far right side, which is basically they tend to feel that SAGE2 provide a better experience compared to the projector model. Now, if you compare it to Zoom, you can see the Zoom, I think it's a little bit better than the classic projector model, but it's not that different. So there's something qualitatively lost by using these kinds of media that SAGE is able to capture. And that's why we feel it's worth looking into. And we recently published these findings in a paper that's going to be out in November. I bet the citation is there too. So read up on that if you're interested. Now, I guess another telltale sign that people like what we're doing is that we have about 800 SAGE walls around the world now. These are just a number of them in different parts of the world. And we counted like approximately 4,000 users using them. And so let me back up a little bit here and sort of tell you a little bit about why, how SAGE evolved and where we are now with SAGE 3. So back in 2004 was the first time we invented SAGE. And back then, Facebook was also invented. And SAGE had to be driven by a compute cluster that cost between $500,000 to $1 million. This is what it looked like. The displays were pretty small and they were giant borders in front of them. Fast forward 10 years later, the only exciting thing that happened in the world was the ALS Ice Bucket Challenge. Just kidding. And this was also when SAGE2 was born. And this was born at a time where JavaScript was just starting to have enough graphics power to do something useful on the browser. And so instead of writing everything in C++ codes, which was what we did traditionally, we switched entirely to a JavaScript implementation. And SAGE was essentially one giant browser window that we controlled with code. So this display wall running SAGE2 is essentially one giant Chrome or Electron browser. Back then, the major breakthrough was that you can now build tile display walls with single PCs. Now, and then you're talking about $100,000 to $300,000 for these systems because the displays were what were expensive. Also, in 2014, we were starting to see this shift from grid computing to something called science portals and gateways and the emergence of cloud computing. Okay, 2020, COVID. That's when we were funded by NSF to continue the SAGE project into version 3. SAGE 3 is now based on TypeScript and Python. Python partly, well, to a great deal because SAGE 3 involves a lot of artificial intelligence capabilities. Now, because of COVID, we couldn't go into the office. So this is my office at home. So actually, if I were to take my laptop and turn it around without pulling all the cables out of my laptop, this is what you would see. During the pandemic, I bought myself two 45-inch screens, and each of them were $240. So for $500, I had a display wall at home. And this was also a time where everyone is using Zoom more and more. And so when we started designing SAGE 3, we realized that the work that we had done in architecting SAGE 1 and SAGE 2 could not move forward into the future, and we had to rethink it. And so we re-architected SAGE 2 from the ground up. And this is pretty normal in computer science. So, if you ever have your advisor, if Steve ever tells you, the code that you write, you're going to throw it away in a couple of years. And, or you just finished your PhD and you wrote a whole bunch of code for your PhD, he'll probably tell you, you'll probably rewrite it 3 or 4 times. And, usually you're shocked. I was shocked when I was a PhD because I thought, wow, this is it. This is the highest pinnacle of my code, my work. And actually it's not. What you find that as a computer scientist, because the field is moving so quickly, you will constantly be reinventing yourself. And so what we also had to do was redesign the user interface for this post-pandemic reality. And what that means now is that SAGE is designed so that you can stay at home, work on your laptop, use even a small laptop screen to place information on a display wall, a virtual display wall, zoom in, zoom out, look at stuff, but also create this virtual space, which actually works on a large display wall at work as well. So that means now you can have your cake and eat it. You can go to work on a large display wall, put stuff everywhere, come home, connect back up, and you still have that same display wall in a smaller form factor. Or in a larger form factor, if you decide to buy two, 40-inch displays, either for work or for gaming. They're awesome screens for gaming, obviously. But the third component is AI, right? AI is transforming everything, both in our lives, but also in the field of data visualization. I mean, nowadays you see a lot of work going on involving this marriage between artificial intelligence and visualization. And so in SAGE 3, what we're working on is two things. One of them is how to use AI to make the user interface more intelligent. Make AI a collaborator in a meeting to help you manage the content, to reduce complexity that you create, that you put onto the wall. The other aspect of it is how do you take a lot of the emerging AI capabilities and make it easy for non-computer scientists, non-experts to use, right? So that—
Sorry, I don't know that.
Sorry, that was Siri, that was Alexa. So that if a user drags and drops a document onto the display wall, the AI, like a normal person who's sitting next to you in the collaboration, will start working on that data and trying to interpret it and come up with new insights. So in a nutshell, that's our plan for SAGE 3. We have a working prototype. If you really want to play with it early, we're starting to release it to a few close friends. So I consider Steve one of our close collaborators, so happy to share it with you guys. But the user interface is constantly improving. And so if you can wait till about supercomputing, which is like mid-November, we're going to do a broader release for people to kick its tires and play around with it. So some of you might be thinking, well, why do you even need these big displays? Why do you need a laptop even? Why couldn't you do all this in virtual reality? Right? And this is my background. When I was started as a PhD student, I worked in Chicago, and I developed software for the Cave. Right? The Cave is this virtual reality room. You project 3D imagery, and then you're like totally immersed. I developed like the first application to connect the Cave to a supercomputer to take supercomputer simulations in real time into the Cave for visualization over a network. And then in 2021, I developed the Cave 2, which is basically the first time someone had tried to build one of these fully surround immersive environments using flat panel LCD screens. And to do that, we had to custom manufacture these displays. And then when I moved to Hawaii, I used OLED, organic LED displays, because they had much better color and contrast and brightness than any of the displays we had used in the past. And because technology advanced far enough, I could get 4 times the resolution in this system, which we call Destiny, compared to the Cave in 2021, and literally at 1/4 the cost, which is pretty darn amazing. So back to virtual reality. So everything here you see is still on big displays. What about working in, say, at home if you don't have the ability to put a really big display? So one of the projects that we've been working on is SAGEXR, which I guess the best analogy is the project room in a briefcase. Or if you're an Iron Man fan, remember in Iron Man 2, Tony Stark sticks his hand into his suitcase and then the Iron Man suit pops out and wraps him in it. Well, this is kind of the same, except you're home now, you have a virtual reality headset, and now you get to stand in front of a large display wall. And what's better than that is you can potentially connect in multiple display walls. So you can stand at a display wall in Chicago, you can stand at one in Hawaii, all within one virtual space. So I'm going to roll a little bit of video, there's no audio, and just talk through some of it. So one of the things we had to do to make this usable was that, people need to type in VR, and people also need to be able to sit comfortably to work with long periods of time. So we took a physical desk and we sort of digitized it to the correct dimensions. We put a tracker in the corner so we could track it. And likewise, we took a chair, we scanned it. We also put a tracker on it so the computer would know exactly where the chair was, so that there was perfect correlation between the virtual and the physical world. So that way, if you sat, you didn't fall over because you could actually see where the chair and the table was. And then the keyboard, we did the same thing. We put a tracker on it. And so whenever you move the physical keyboard, the virtual keyboard would move. Now, the problem is, how do you find your fingers on the keyboard? So to do that, we put little contact sensors on the home keys, sort of hoping that most people can touch type, right? And so here you see someone using SAGEXR. The image in front of you, the top image, is basically a virtual version of a large tile display wall. The little panel below is kind of like a user interface for manipulating some of the content that's on the display wall. But you can also do, as you can see, direct manipulation directly onto the display wall. And part of the reason for having those two kinds of user interaction models is because those are the two models that the classical SAGE2 supports. And we wanted to provide this capability for the end users to see what they would use in a virtual environment. Right? They could transition from something they were familiar into something that's potentially new. Now let me fast forward a little bit, and you can see there's more content now showing up. And then at the same time, whenever the large display wall is connected to, is manipulated and changed, you will see all those change happen in the virtual reality display wall as well. So we did a quick user study of this. And basically, we found that the things that typically people did in front of the display wall, they contribute information, they organize information, they validate information, they annotate information, they create chronicles, they basically save away versions of the layouts of information. All these things they were able to redo inside a fully virtual environment. The interesting thing was we found that even though they were in a room that had maybe about 20 by 20 feet of space to work with, of physical space, the amount of space they actually used in virtual reality was much larger. So that sort of told us that if people had more space to work, they would take advantage of it to lay out information. In fact, they use twice as much. And the cool thing about working in VR is that you're not subject to gravity. So that means that you're going to see layouts of information in space that you normally don't get to do in front of a standard display wall. Oh, I forget to mention that in the SAGEXR, anything you see on a display wall, you can peel off and put it into the virtual environment as its own floating visualization. So by being able to do that, you can create these giant elaborate postings in 3D space of information. We certainly found that having the 3D track furniture is extremely helpful, because no one is going to work in a VR environment standing all the time. Well, maybe if you're trying to get exercise, or if you're used to working in a standing desk, right? And then, the final finding, I guess, is once you go big, the question is, can you even go back to being small? I find, for example, at home, when I started using 2 large displays, when I go to work and have to work in just a small laptop, like when I'm on travel, it's really difficult to work because you're just so used to using all this space. So maybe in the future, as the resolution of head-mounted displays gets cheaper, as the power consumption goes down, the computing goes up, where you don't have to carry all this heavy gear or battery pack and things like that, we could potentially see this kind of technology completely replacing a laptop even. So that may be 10 years out or something like that. So it's a pretty exciting time to do this kind of research. So I mentioned this partnership with artificial intelligence. So in 2004, I did some work in trying to teach a computer how to understand natural language to produce visualizations. The joke I always tell about this is that the goal for this research is so that I can retire and not have to talk to scientists anymore, because my AI will talk to them and make all the visualizations that they want. I think the reality is this idea came to me because I was talking to a geoscientist. And basically the geoscientist told me this, and this is important for all you computer scientists who develop tools for scientists. They said, your tools are really difficult to use. And what he meant by that was, it takes a large investment in time for any scientist to use a powerful tool. The question they always have is it worth my time and investment in learning this tool versus the payoff that I get from using that tool? And he said, wouldn't it be really awesome if instead of having to learn how to do Jupyter notebooks or whatever, all these complicated user interfaces, if I could just do what I do with my graduate student right now. And if I need a visualization done, I will say, graduate student, make me a chart of X, Y, and Z, right? And then the graduate student goes away, he comes back, and at the next meeting, he has the charts that the scientist wants, right? And so, aha, we can try and replace the graduate student. So this was what got us on this track of, can we teach artificial intelligence enough to actually make visualizations? So I'm going to play a short video of a prototype of Articulate.
Where is COVID risk at its worst? Show me cases by date. Show me the correlation between COVID risk and cardiovascular disease.
So the thing to note here is that RJ, who's my master's student, he's not explicitly saying what kind of chart he wants. He's not saying, make me a bar chart, or make me a line chart, or make me a, whatever, right? That's easy to do. What's harder to do is to try and figure out, based on what he's saying, what is the best chart to produce? What are the right attributes to use to make that visualization? That's the hard part. Now, to make things even harder, so this research that you're showing here, I started doing in 2008. And so in that time, again, using JavaScript APIs and using new natural language processing APIs are making this work a whole lot easier than back in 2008. The next major step we're trying to make is not only just having RJ talk to the AI to produce visualizations, but imagine that this AI were part of a meeting with a group of people, and the AI is constantly listening to the conversation between the people and interjecting by producing the right visualization at the right time. Or if the user is underspecifying the visualization, like for example, instead RJ here, instead of saying, make me a visualization of this attribute and this attribute, during the course of a natural conversation, you might be talking about, well, you know, I think COVID might be rising, particularly in people who have cardiovascular problems. Do you think that's true? You know, and then so RJ could say, well, you know, articulate or whatever, show me a chart. And so articulate is able to listen to all that conversation before to figure out the context to find out, okay, I think if I made a chart of, you know, COVID risk versus cardiovascular risk, that would be the kind of chart that you're asking me for, and it'll produce that. So that is immensely much more difficult. It's an area of research that hasn't really been done yet in natural language processing. Right now in natural language processing, everything is focused on how can we perfectly understand what the user is asking? And what we discovered was all this time, this background talk when people think aloud and so forth, we've ignored, we've kind of thrown all that data out the window. Now we're realizing we should have been paying attention all this time. We should have taken all that data and used it to make the AI more intelligent. And so that is the goal of this next generation of articulate. And then along similar lines to articulate, you know, most of you as graduate students are going to have to read a lot of papers because that's the fuel for new ideas, right? And, you know, Steve probably hands you out, you know, papers to read, or he go, and in various classes you take, they tell you to go and find some papers, read about it, present it, or you go on a reading diet, which is kind of like you got to read a paper or two every week, right? So that you can start feeding your brain with you know, protein, knowledge protein, right? Now the problem with this model is that we can't keep up anymore. There's an estimate that last year, or just a few years ago, 400,000 research publications came out of just computer science alone. And every generation of student has to read, you know, an exponentially larger clump of papers than its predecessor, right? How are they going to keep up? Well, maybe you can read summary papers. You know, there are papers that summarize everything, but even summaries papers take a long time to read and produce, and they're usually, you know, based on old papers too, very old papers, right? So how do you keep up? So in this work that we started on ZExplorer, we set out to design a system where if you grab a whole bunch of papers and put it into ZExplorer, it uses AI to basically create clusters where papers are related, right? Using, you know, things like BERT and so forth, and a neural network that it trains to learn the clusters of the papers. And then what's different about this work compared to other work is that in other work, you're done. You just show the cluster and that's the relationship between the papers. What we do is we allow the human to intervene by saying, you know what, this paper that you have chosen to cluster in this group, I think it really belongs more in that group. And you can interactively move it to a different group, or you can reform the clusters. And what the AI does is that we're building this with a contrasted neural network. So you're able to retrain it for your preferences. So the next time you have a new bunch of papers you throw in, it will tend to classify those papers more to your frame of mind. And so think of it kind of, I guess, like Netflix. When you hit like on certain, or star on a certain movie, Netflix will tend to give you more similar kinds. Okay. So that's that. And oh, by the way, some more statistics. 10 years ago, the average researcher would spend an hour reading a paper. Now they only spend about half an hour. There's just not enough time to read all those papers. And this is just going to only get worse. How much time do you have? It's 7:17, so I'm going to wrap up pretty soon. Don't want to take up too much of your time. So everything I've talked about is in computer science, right? You know, one thing that's important to remember about computer science is that computers, we design computers for humans to solve problems, we didn't really design computers to solve computer problems. We're in the service of humanity, right? And so always think about that. If you build these cool computer science algorithms and techniques, who cares, right? And so, oops, do I have audio on this? Sorry, let me turn the audio off. So the videos that you're seeing is from a project that we have been developing for a couple of years now, funded by the Department of Energy. It's called the Hawaiʻi Advanced Visualization Energy Nexus. And the idea is we have a lot of data about renewable energy, and Hawaii is trying to figure out how do we get to 100% renewable by 2045. That's a daunting task. That means trying to figure out how much wind power to construct, how much solar farm, how many what's expansive solar farms to build. How do we convert automobiles to electric? How do we convert industry to electric? All these kinds of issues. Now, on the mainland, it's a challenge, but not as big a challenge as in Hawaii, because in Hawaii, the amount of land we have is incredibly small. And so, while Hawaii would love to go 100% solar because, hey, we have a lot of sunlight. Why aren't we doing all solar? Well, Hawaii also wants to be food resilient, right? We ship in almost 80%, more than 80% of our food. We don't grow it in Hawaii. We just don't have the space, right? So if we have a giant hurricane or a tsunami, we could be cut off from food supplies for a couple of weeks. And we don't have that capacity to survive if we don't have food. And so people are thinking, how can we make Hawaii more food resilient? Well, it so happens that the best place to grow food is the best place to collect solar energy. And so there are these competing interests that happen. So the Hawaiian Electric Company produced this 4,000-page document with 200 scenarios of how to convert Hawaii to 100% renewable. And the government and the general public was asked to pick one. And so we work with the Hawaii State Energy Office to use our advanced visualization tools to help them look at the data and to show the general public what is the impact of putting all these solar fields, all these wind farms in Hawaii. So for example, this one is in our virtual reality experience. You're flying around Oahu, and what you want to see is how does the placement of the wind farms encroach on the beautiful landscape of Hawaii, right? Well, you can say, well, yeah, but you need energy, whatever about beauty. Well, a huge part of the economy for Hawaii comes from beauty because it comes from tourism. So we can't just sort of dismiss that. And there are people who are concerned about, well, those wind farms are going to be pretty big. And then there are also things like, well, they're going to kill bats and all this kind of stuff. We developed a tool on the right here, which uses tile display wall to basically use them to allow them to compare multiple scenarios simultaneously. We built one of these display walls in their facility so that they can do some of this homework themselves. And then lastly, for the general public are not really into numbers and charts like this. So what we did was we built this physical 3D model of Hawaii, and we projected it with GIS layers. And instead of making them touch a user interface, actually this is the later version of it, we had them take these optically tracked pucks and they could turn them to turn on and off different layers. And this was in a way kind of almost, I would say initially was more, I thought it more of a gimmick, but it turns out this was incredibly engaging for the general public who are not computer savvy. And also, frankly, even though they're not computer savvy, they were kind of jaded by iPads. This was something kind of new because it was retro combined with something new. And so as a result of this, people were, after seeing this, started to ask deeper questions about the data. And that's really important. This kind of tactile nature to the interaction drew people into asking questions about the data. Now, in times right now where people don't believe in data, don't believe in science, and don't believe in information, this is absolutely crucial, right? how do you provide other avenues of interaction that allow people to engage in data in a more user-friendly way that transcends, their background? And so this is the small system that we initially built. This one is like twice as big, like 6 feet by 6 foot. And then this was designed for the Hawaiʻi Electric Company for a conference in Hawaii. Okay, my last slide, and I'll be on time. So, in Hawaii, we have large numbers of indigenous populations, who basically, were there before everyone else was, and we want to respect their needs and also help involve them more in the sciences and in the work that we do in computer science and science in general. And so this year I created a new lab at the new Academy for Creative Media building. This is a sort of a fly through of the building. And it's called CreateX. And the idea behind it is that here we're combining computer science knowledge, we're combining indigenous knowledge, we're combining creative media techniques, and we're combining science to create the space that allows students to explore what can come from this fusion. There's a lot of history, there's a lot of knowledge embedded in indigenous practices that we're only scratching the surface of. The sensor networks that we use to study the weather only came about probably in the last 20 years. The indigenous populations have been here for 1,000 years. And so if we can tap into some of that history, we could potentially fill in some of the holes in the data that we have. And so we're pretty excited. This one particular application is called Valki'i, which is basically, it's a view of a landscape in Hawaii. There's a touchscreen interface, and in it, you learn Hawaiian by taking these language tiles and putting them on the screen. And if you put them in the right order, and it'll actually help you put them in the right order, you will teach, here's AI again, you'll teach the little bird what to do. It'll fly, it'll walk, it'll fly happily, it'll walk sadly, those kinds of things, right? But there's no English at all. You have to figure out by placing the tiles what it's trying to say through animation and through the Hawaiian words. And so this is a way to not only teach Hawaiian and get Hawaiian kids interested in technology, but also at the same time, because they're moving these tiles to control animation, in a sense, they are programming, which also creates a gateway for them to be interested and to see that computer science isn't this alien thing that has nothing to do with them, or science is this alien thing that has nothing to do with them. I mean, the indigenous population here have been doing science all the time. They just haven't thought of it as the way we call it science. And so this tends to be this separation, this alienation. So anyway, and one of the classic, perfect examples of indigenous technology is the surfboard. So I surf a lot. Surfing is basically invented here in Hawaii. And so the first surfboard was these giant wooden boards, right? So that's an indigenous innovation. Okay, I'm about done. Want to really appreciate you for your time. This is a little photo of my lab, which is always evolving as students graduate. Yes, we have a lab dog. His name's Clyde. We promoted him to staff now. So if you have any questions, I'm happy to answer them.